Great. So, yeah, this is an APL coding stream. We'll be looking at some advent of code problems from 2017 as a warm up leading to the 2020 competition. As I said in my last stream, I'm gonna attempt to be competitive this year, although we'll see how that works out. So my plan, at least for right now, is more or less to be streaming every night from now through December 24th. So the first Advent of Code 2020 problem, at least in my time zone, drops Monday evening, I think. Yep. And yeah, we'll do some warm-up problems today, tomorrow, throughout the weekend. It's a long weekend for those of us in the United States, so happy Thanksgiving, by the way. Um, so yeah, I think we'll just take the opportunity to go through some old problems, warm up, identify any weak spots or helper functions that we want to build leading into the 2020 competition. Um, and hopefully you guys can learn something about APL and uh, see what it's all about. So let's get into it. I do want to mention one thing from my last stream. So last stream we did problems 1 through 5 um, for Advent of Code 2017. And I said several times something along the lines of, uh, here you can see in my problem 1 solution that I'm doing this like interim variable assignment because I didn't want to use the selection operator in a train. But you can actually do it. So if I just get the same answer here, you can use selection operators in a train. It's a little bit tricky. So if we made this whole thing a train instead, this would be, yeah, so this is equals reduce, sum reduce, and then if you want to use the selection operator in between, you have to, I think the selection operator has to be commuted, and then it also has to be in parentheses like this. Um, but yeah, so it's just a little bit trickier to use um, than I wish it was, honestly. But I may be using that in the future rather than this sort of interim variable assignment because naming things is hard. Anyway, that's the only update really that I wanted to give from our stream last time. So without further ado, by the way, just before I started streaming, um, I think they did a deployment or redeployment of the site. You can see they have a star count here in the event, uh, the event page. I don't think this was here before, but it's pretty nice. You can see your total stars for all the different years. So yeah, and again, just as a refresher for those of you who didn't catch the first stream on Sunday, we are looking at problems for which I already have stars, at least some of them. We'll look at 8 and 9, which I don't. So you know, I'm not saying I'm going into these blind, but I have looked at these problems, I think sporadically kind of over the years. I've solved them in languages other than APL. Um, so, I like the 2017 problems, and I thought that they would be, um, they're good examples of sort of the methodology that APL brings to the table when you're trying to solve these different Avenue Code problems. And the code that we're going to write to solve these problems is going to be posted um, on GitHub, and the link to that is in my Twitch profile. So, anywho, okay, so with all of that out of the way, let's go to problem 6 and dive into this here. So, uh, debugger problem here is having an issue. Any number of blocks. The bank with the most blocks is chosen for redistribution. Um, So being chosen for redistribution basically means we zero it out, I guess. And then redistribution starts at the next index. And we just keep going. What happens if there's a tie? Oh, okay, so there's a tie. The first bank wins the tie, and its 3 blocks are distributed evenly. Okay, well, all right, so let's get our problem input. Get 2017 6, right? I thought I set up my cookie beforehand. Well, all right, I'm not gonna do that on stream, so I guess I'll just save this as in 6.text. Great, so this will be then inget in/6.text 1. Okay. And then it's just the one line apparently. So we'll parse the digits out of it. DW membership partition close left. Syntax error. Yep. All right, we're just getting warmed up here. Rank error now. Right. All right, for each execute, this is going to be PT. And then, what are we actually doing? So we're going to write a function that operates on this. And I want the index of the maximum, which is going to be take grade down, is, this is apparently, this is now optimized in dialog 18 if you use the top operator. New index, or max index, I guess, and then the actual value that's held at that index. Right, yep, nothing wrong there. And then we want to take the max index plus iota max value, right? Syntax error. Right, so the max index it's saying here is at 13, which seems right because the 15 is there. How long is this? 16, sure. What's my index origin? 1. Okay, great. And then we're going to want to be an IO0 actually, because what we're going to do now is we're going to mod this against the length of W. This has to be 1 plus though, because we're in IO0 now. And we want it to start allocation on the next one. But now, so it's possible that I have overlap. So what I want to do is I'll use the key operator and concatenate jot length, like so. Then if I split these are now my new indices and my new values, right? And now we're going to say for W at max index 0, so we're zeroing it out. And then at the new indices, we are placing new values. Rank error. Oh yeah, sure, because I didn't do transpose split, like so. Well, that is not true at all. So if I do plus here, is this smart enough? Yeah, this looks correct. So if we look at PTs and we look at this, let me actually test this against one of the test cases. 0270. Oh geez. 2412. Yep. Okay, I can get rid of this. Run this twice. 3123. Right. 3 times 0234. 1341. So we're resolving ties correctly. And then finally for 5, 2412. Okay, great. So what are we actually doing? Oh, there's an infinite loop. Given the initial block counts in your puzzle input, how many redistribution cycles must be completed before a configuration is produced? Okay, sure. So we're going to start with an empty list. And we'll say if enclosed W is in the accumulator, then just give the length of the accumulator. Otherwise, accumulator gets enclosed W. And then recurse. So the answer in this example is 5, 0270. Take the power operator out. Right. Okay, great. So this is not super efficient because this membership check is it has to do a linear scan each time. Unfortunately, APL doesn't really have hash tables, but usually it's like fast enough that it doesn't really matter. So we get 12,841, which is the correct answer. And then the question is, out of curiosity, the size of the loop, starting from a state that has already been seen, how many block redistribution cycles must be completed? Okay, I see. Well, so we have this accumulator. Oh, I shouldn't have done that. It takes a long time to print to the screen. But the length of the accumulator is 12,841. And if we do accumulator index of enclosed PT, oh. Well, wait. So the last element of the accumulator is going to be, it will have been in a loop, right? Oh no, it won't. Okay, so we'll modify this. And we'll put the accumulation after, or the check after. And then this will be -1 plus. Well, yeah, that makes sense. Okay, well, what if I run this and so I do acc index of enclosed W length acc minus, and this should be 1 plus because we're 0 indexed. $80.39. Ooh, 1 off. Apparently we don't need the 1 plus. $80.38. Okay, well, so getting warmed up here definitely. Let's see if we can't arrange this in a nicer way, and I can explain what's actually going on. So we'll edit to, no, this is problem 6. Dialog. I do want to create it. And so first we're parsing the input. And that's like this, which we'll actually just call P. And then part 1 is this. It's a really long line. Then part 2 is this. And so what are we actually doing here? Basically, let me step through this function kind of point by point. So first we have an accumulator that starts with the empty list. And we're going to be, as long as the element that we're evaluating is not already a member of the accumulator, then we will append to it. Again, this membership check is essentially a linear scan, but it's usually quite fast. So for the sizes that we're dealing with, it doesn't really matter. Next, I get the index of the maximum element and the corresponding maximum value from our array. Then I do iota, which gives you a range of numbers. So in index origin 0, it'll start at 0. So I ask for a range of numbers from 0 to whatever the maximum value is, non-inclusive. So like if the maximum value is 5, I get 0, 1, 2, 3, 4. And I then add the index of the where the maximum element is. Basically, my plan here is to identify a series of indices that I'm going to change our input array at, and then corresponding numbers that I'm going to be adding to those array locations denoted by those indices. And I do that with, so I use the modulo operator. So we're doing modulo the length of our input list. And that means that once, my range grows beyond the length of the list, then it'll kind of wrap around back to the beginning. It'll start at 0 and then go up. And the only other thing is that I have this problem where, so we saw this in our sample input. We have this 0, 2, 7, 0. So 7 is the maximum element. So we're gonna zero that out, and then we have 7 that we kind of redistribute across across all the blocks. But it's going to 7 is like longer than the length of the list, so there's going to be parts of the list that overlap, maybe even multiple times. And so when I'm adding numbers at indices, I have to group together all the indices that I have so that I can add everything in one pass, right? And so I use the key operator to do that. And so I showed over here that it looks kind of like this for the first time that we run it on PT. If I ran this on our sample inputs of 0270, I get something like this, which is basically saying like, hey, at index 3, add 2. At index 0, add 2. At index 1, add 2. But at index 2, add 1. So you can think of this left column as my new, or as the indices that I have to add at, and then the rightmost column as the values that I'm adding to those indices. And in order to split those out so that I can work with them separately, I do a transpose, so it kind of makes the array horizontal like this, and then I split them. And then you can assign those to variables, like I'm doing over here. So I have our list of new indices and new values, and then I just say, all right, so at the index of the maximum element, zero it out, because we're picking up its value and reallocating it elsewhere. And then at the new indices that we've calculated, add the new values, and then recurse. And a reminder that we have tail recursion in dialog, so this isn't really much worse than a standard loop. So that's the idea, and this is, this is quite a long function. And I think, so the only difference with the second one is this sort of return value. So in the first case, we're just returning the length of the accumulator, or basically how many elements we've added to it so far. And that's the answer for part 1. And for part 2, we are saying, hey, give me the index of the first occurrence of this element that's duplicated. And then once we have the index of the first occurrence, we can just take the length of the list and subtract from that index. And that will give us kind of the length of the cycle between the two occurrences. So I'm pretty sure that there's a way that we can just calculate the list once. Yeah, I could do, yes, so I can actually add W to the accumulator. And I tried this just a few minutes before. I can't do this I can't do this in the general sense before my check because otherwise it'll just, uh, it'll detect that our arguments is already in the list and it will immediately terminate, which we saw. But I can add to the accumulator here, and then I can just take the length neg1 plus, and then this becomes part 2 is just neg1 take the accumulator, accumulator index, length accumulator minus. And actually this can all be a train. I am reasonably sure, so we can just say neg1 right tack length, like so. Let's see if it works. Oh geez, cancel, cancel. Yeah, it's fine. So what do we got? So I got 0 over here, which is sort of interesting. But I got 8039 over here, which is again 1 off. Huh. Who would have thought? Alright, so this will be neg1 plus. That's 8038, so we'll add that to our answer. But then what's going on here? It's not giving me the what do I need, a right tack here? Length, huh. All right, how about a left tack length accumulator neg1 plus? 12841, except that, well, is that actually correct? Yes, it is. All right. Well, we can rearrange this so it looks at least halfway legible. This can go on this row up here. And this function can be split onto multiple lines unless yeah, so we can do like f this now runs on P, so we just do fp, and this is part 1, and this is part 2. And I believe that will run. Or not. Right, I forgot that you can't do multi-line functions from the REPL. But we can edit them. And now I can run this line and this line. Oh, yeah. This is now like so. Yeah. Fair enough. It's pretty good, all things considered. So we avoid having to do any recalculation for part 2 because we have our accumulation array already from part 1. There may be multi-line function. I don't do multi-line functions a lot, but sometimes they're really good for, I don't know. Sometimes you just don't want your entire function on one line. So yeah, I'm going to say this is fine. Only say file to disk. Yeah, great. All right, let's move on to problem 7. Recursive circus. It's holding a huge disk. This looks like a, yeah, it's a tree. Name, weight, and the names of the programs immediately above them. Okay, so this describes a tree, and each node has this sort of metadata, weight. And they want us to find the root. All right, fair enough. Save link as 7. So inget in /7.text1. Okay, so if we're just finding the root, the root is essentially it'll be the node which no other node points to, right? So if we parse this out, we can use 819 ibeam a to get a list of lowercase characters, and then we say membership partition enclose left, and again should be like this, right? And then we can do a train here, and we can say take concatenate enclose drop. Yes. So this takes the first element and puts it in its own column along with a list. The second column is a list of everything else. And we are going to call this P. I'm going to, wait, I need weights as well, but not for part 1. It doesn't seem like. So this is literally just going to be take the rightmost column of P and concatenate everything together like this. This is everything in the rightmost column. And then we just take the leftmost column of P without that. And this gives us all of the elements in the leftmost column without all the elements in the right column. And yeah, RQWGJ. So that's the answer. Okay, great. The programs explain the situation they can't get down. One program has the wrong weight. All programs above it must each match. So the sums should all be the same, and then at some point in this tree, we have a situation where one of them is different. given that exactly one program is the wrong weight, what would its weight need to be to balance the entire tower? Alrighty, we can put together a graph. Now I'm sort of a little bit weak on graphs. It's something that I want to work on before the competition in 2020 actually starts up. But yeah, and then if I take the rightmost column of P, this will just be for each ID's jot index of, right? Still an IO0, but I don't think that matters. So this is our graph, and the way that or a common way to represent graphs in APL is just a vector where each element in the vector represents a node, and then if the node has indices there, it means that there's a connection from one node to the other. So, I need the weights. It's not in P. So in 7.text again, let me see what I got. Right, for this one, I want to pull out the digits. Membership, partition and close, left tack, digits for each execute. No, actually, if I replace this, yeah, okay, great. This is weights, which I'll call W's, I guess. So what's the deal? So one of these towers has the wrong weight. The way that we know it has the wrong weight is if it doesn't match, its siblings, the weight of its siblings in the tree, right? But actually, so what I'm thinking is that we can calculate the recursive weights. Like we can basically do a depth first traversal and figure out the recursive, like the additive weight of all these different nodes. But the trick is we need, like if we do that, the weight difference is going to be propagated up to the root. So we need a way to, like we only want to look at the node differences that are furthest down the tree. So what I'm going to do is I'm going to have two vectors actually, recursive weights and depth. And that will be the 2-row enclose G for each 0 using the new constant operator. So now we just have a bunch of zeros. And now we're going to write a recursive function that starts on our root, which is going to be ID's index of enclose this guy, right? Yeah, this is the ID of our roots. How many elements do we actually have in G? 1078, all right. And the function is going to be we're going to index E into W right, disclose for each recurse, and then but I need to keep track of depth. So depth is going to start at 0, and then this is going to be alpha plus 1. And we'll call these our new weights, right? And then recursive weight W is going to be equal to the sum of the weights of all of your children plus weights plus your assigned weight, right? And then the depth is going to be equal to alpha, and we will return like so. Sure. Well, I don't have a base case, but I sort of didn't expect this recursion. Oh, that's right. Okay, so a weird quirk of APL is that when you use this each operator, even if the list is empty, the function runs at least once. And it apparently does this to get the prototype of the empty list, because not all empty lists are created equal. Some are like empty strings, some are whatever. So so what I need to actually do here is if weight G 0 equals length, then return like this. Still, huh? Oh, disclose. Aha, okay, and now we have recursive weights. We also have depth. Some of these are, wait, 0. Oh yeah, because the assignment happens later. Hmm. What if does this still happen if I do it like rank 0? Apparently yes. All right, fine. RWS W assign WS plus slash in WS and oh, actually, sorry. This can just be like this. Depth DW gets assigned alpha, and lastly, we return, yeah, like this. But now I need to row enclose 0 for each G. Hey, we got all the recursive weights filled out. And we have depth. So, the question is basically, if we look at P, even better, let's look at G. And then we want groups where the recursive weight is different. So, for each enclose W, index into recursive weights, like this, right? Yes. And then we want for duplicate elements, right? So this is going to be, what do we call this? NWTs? I don't know. Naming's hard. For each one of these, we want where 1 does not equal the length of the unique, right? Ooh, okay, this should be one is less than, because I have empty lists in there. And then 1 is in there somewhere, right? Yes, it is. So now I can take NWTs like so. Nice. Okay. So we can see we have some differences here. And okay, if I do this like so, and I index that into our depth vector, 102. So this rightmost cell here is the discrepancy that happens at the lowest depth. And it looks like it's that last number. It's that last number that needs to change. So the index of that is 1077. And this number that needs to change is index 310. So the weight, I'm doing this all by hand, but the weight is 341. And the difference here, 1398, 1406, this needs to come down by 8, right? And so if we take its assigned weight of 341 minus 8, we get 333, which is the answer. Okay, but I did all this manually. So now comes the tricky part, which is how do we automate all of this? So let's take a look. So this is, which problem is this? 7? Day 7. I do want to create it. So first we're doing kind of some interesting parsing here, right? This is so we can call this P. Actually, I think we can, hang on. if I take digits and put it on there like this, I'm just trying to do all the parsing in one shot. Now I can do 2 to this kind of interesting function here where it's take catenate ja enclose drop, right? Now I can mix. Right. Okay. Yep. And let's say that this is P then. And the answer to part 1, which we actually need later, by the way, to determine our root, is no, I scrolled up too far. That's just this, which should still work with our current. Yep. We can disclose it. Um, I'm going to assign this R for root, and then if we just echo it, that'll be part 1. So both of these together should give us that answer, right? And now we have this recursive function here. I also have to assign weights. So this now becomes ID's index of R, well, enclose R. Oh, it's already, yeah, we can just do that. And so weights needs to be P first column for each execute, right? Yep, numbers. And then we can do this naming on this row. So we're sort of initializing our recursive weights and our depth vector. We're just initializing them with zeros. And then can this be cleaned up? I mean, this is kind of a mess here. So I'm saying if this doesn't have any children, then we just take its assigned weight that gets put into its recursive weight, and its depth is whatever alpha is currently. Yeah, and I can't reuse this because I do the recursion later. This would be much easier if it just didn't run the recursive function. Yeah. Well, okay, let's pretend that this is fine as it is. How many columns is this? 97? That's not the end of the world. You should see there's some people that write there are some people that write like APL or K especially, and they have really long lines. You'll see their source code, and sometimes it's like 100, 120 characters. It's kind of interesting. So, but now what? Okay, so assuming that we run, can I just, okay, so copy, paste. Yep, great. And then, um, now I have my recursive weights, I have my depth, and I have my graph. And what we're saying is that first of all, we're finding, it's this kind of thing where we're finding um, we're finding discrepancies in the recursive weights. What does this NWTs actually signify? Oh, I see. Yeah, so we need this. And more specifically, we need if I took recursive weights and put it on top of depth, that's not really what I wanted. Huh. I can transpose this. Now what? So we have this, and then I'm trying to find the maximum depth. That looks like this line here. So we can call this discrepancies. Naming things is such a trip. And then rather than this whole thing, we just have discrepancies here. And I want you to tell me the index of the max. Check this out. This is getting convoluted. Index. Right? Okay. Now what? Now I want you to, we have to find the element that's different than the others, and then we have to get the difference. Then once we have the difference, we can apply it to its assigned weight. Um, This might have been easier to just do recursively. So rather than like calculating the new weights and the depth vector um, beforehand, we could have just done a recursive depth first traversal and said like basically look at all the sibling elements at one time. No, whatever. So like this. Actually, I want this the other way around. And I want you to like so. Yep. And then take the rightmost column and do a minus reduction. So this is the difference, which we saw actually. And now I just need to get the native weight. The discrepancy should be, so we'll call this diff. And then discrepancies has a number of indices. Um, for a problem that's fairly easy to solve manually, this is very tricky to automate. So what did our index actually be, or end up being that we had to modify? It was 311 or 310, 1077. Okay. All right. NM new max. And then if I take iota discrepancies NM index, this gives me the index that I need to be in for G. $13.98, $14.06. Um, so we'll take this line and look how short the part one solution ended up being. Oh, those are good times back in part one. um, so now where discrepancies where index new max. So I have, but now the hmm. The trick is that I need to find in this index the um, so if I go back to this key here, this basically the lowermost element is going to be the one that I want. Right, so this can be like count, and then yeah, difference will still be like this, but for this one, this is going to be new indices, like so, and then I take yep, index of right tech count 4. And then we can take this, right? And then we can take weights, diff plus, and that's our answer. All right, well, we got there eventually. So this is like so, then like this. And if we run the whole thing, we get, yes. Part 2. All right, so I hope you followed all of that. I'm not sure I did. I think the tricky thing here is just finding, um, so the problem with doing like a normal sort of depth first recursion is you want to bail out early if when you encounter these sort of recursive weights that are different. Um, and this is, and then there's this thing where you have to like find the elements that's different and then track the indices and all this stuff. Anyway, I'm sure that this can be cleaned up significantly. I'm not going to submit it like this, but at this point, I think we're ready to move on to another problem. All right. So we've got part 8. Heard you like registers. This is like a parsing thing, really. Um, what is the largest value in any register after completing the instructions? So which conditionals do we have? Greater than, less than, greater than, equal, equal, equal. We could also encounter these, so 6 total. And if we decrement a negative number, it means add. Okay. Let's get our puzzle inputs. Hello, I like J. Probably would like APL too. Which problem is this? Say beep if you read the chat. So I don't have multiple monitors, so it's difficult. Let's look at this guy's J solution. He doesn't like how wordy it is, which is great because I don't like how wordy my APL solution is. 8.text. Yeah, sure. Significantly less wordy than mine. So I don't know if people are familiar with J, but it's an APL like. Um, Actually, J in a lot of ways is more. How do I put this gracefully? I think it's more consistent than APL in a lot of ways, in terms of leading access agreement. There's stuff like split in APL is rank 1, instead of being like rank -1 or operating on the major cells. I just So I really like J. The only thing is, I just don't like ASCII as much as the glyphs. The glyphs are actually really nice. So, but this looks like a great solution, man. I only know a little bit of J, but I think that this problem is, or problem 7 in 2017 is like deceptively tricky to do in an APL-like language. So I wouldn't worry about it. We're in the same boat. And now I'm about to do a parsing problem, which is also something that APL is not. Well, no, I shouldn't say that. It does pretty well. You just got to know how to do it. So look at this. It's not 8.dialog. It's 8.text. I wonder if that person is still here. No, no one will know. I'll try and come up with a better solution to interact with chat in a more timely manner as the days go on. Okay, so I think what we're going to do for this one is we're just going to split on spaces. So does not equal like so. And then I can mix this actually. Right. And each one of these is structured the same. There's always this if statement and always a decrement, increment, whatever. Okay. I don't know if we need to mix. I don't think there's anything interesting here. No, I take that back because so if I take P index 0, 0, 1, 2, 3, 4. Yes, this is a list of all the registers that we have. And there's not very many. So this is just going to be regs. And then reg vals is 0. Right? I'm pretty sure everything starts at 0. The registers all start at 0. Okay. And then what are we doing? So P rank 1 P. I'm immediately going to give up on this and write a multi-line function. Because I don't think this is gonna be super pretty. So okay, so what do we got? We have dest op val condition reg condition op condition val is equal to w 0, 1, 2, 4, 5, 6. Like so. And we are going to do some modification if the condition is true. So cons is going to be oh dear. Creg val call this CRV is enclose creg regs index of reg vals. And cval should be execute cval because it's a number. So then this is going to be CRV greater than cval, CRV less than cval, CRV greater than or equal cval, CRV less than or equal cval, CRV equals cval, and CRV is not equal to cval. And let me just make sure. So if this is F, and then I do one take P. Interesting. I'm in IO0, so what's the problem? You don't like oh, right, this is a matrix. So I do have to do rank 1 here. And I get my conditions back, and everything's happy. Great. So, um, cops is going to be a bunch of strings. So we have uh, greater than equals, less than equals, equal, and not equals. And these guys here need to be lists instead of single characters, like so. And now we're going to say if cons well, so conditional ops index conditional op, and then index that into cons. If that's true, then we're going to do some state modification. And now we'll say val also equals execute val. And we'll say at is going to be reg vals maybe I don't have to use this at syntax. I think perhaps I do. ERV. Well, anyway. This is regs, index of the destination. And this is going to be, we're going to add some value. That value is going to be inc dec index of op, right? This gets indexed into 1 and -1, and then that will be multiplied times val. So basically, if it's decrement, then we're negating, and then if it's increment, it's increasing. Right? Let's try it. The debugger is pretty good. Surely this will be fine. Invalid token at the time. I've never seen that error before. That's very interesting. Oh, I'm missing a, yeah. What is this? Nope. Missing one of those. All right, fair enough. Length error, cons, copsci cop, cop's index of cop. Sure, well. Yep, this should be in close. And that should also be in close. Index error. That should also be in close. Oh, we're learning a lot here. Oh, interesting. Dec. We're dec D if OIY is less than or equal to 1, which it is. D is indeed the first register. Okay, great. So now, we just have to reset regvals. So regvals, 0 constant operator regs, rank 1, the whole thing. Oh, yes, of course. So now this has to get assigned back to regvals. All right, great. And the question was, what's the maximum? 5966. Yeah. All right, cool. The highest value held in any register during this process. All right, there, part 2. Okay, here's how I think I want to play this. I want an accumulator that's length regs, 0 cons, 0 row commute. And the shape of the accumulator is, so this is going to be a matrix. And then we're going to say that this is equal to new values. And accumulator is going to get concatenated with new values. And meanwhile, if the conditional is true, no, dang. That won't work because we need to do that. We need to respect the conditional even when we're accumulating rows like this. So, okay. So we'll say nvs like so, nvs okay. Right, that looks promising. Now if I sum the accumulator and then I take the max, I should get the same answer as before, 5189. It's not the same answer. It's close to the same answer. And if I look at the accumulator, deck negative 186, if whatever. Um, hmm. Well, no problem. Rather than having a separate, or yeah, we can just do can assign regvals, and then we can say gets regvals like this. Right, and now if I take the last row of the accumulator and I max it, now I get the correct answer. So now it's just Ravel accumulator max 6347. Yay. All right. What are we doing on time? I think I can manage one more. You're sure this is a real programming language and not just some preposterous variety of moonspeak? Oh, it's Eric Wassel. What's up, man? I missed you dropping in, but thanks for admin code. It's great. Maybe you'll see the recording. Okay, last problem, stream processing. Server group, you'll find garbage. What does the input look like? Yep, that's a lot of garbage. Okay, fair enough. Well, so let's download our input. And this is problem 9, is that right? Yeah. And the question is basically like, how do we determine nesting depths while also taking care of garbage? I think. Oof. All right, so I don't like to use regular expressions that much because I don't think that they fit the ethos of APL. But sometimes they are the right tool for the job, and I think they are here. So if I do replace exclamation dot with something like this string here, right? Okay, yeah, that's what I want. So I'm replacing exclamation plus any character with the empty string, and those substitutions get applied in order. Yeah. Okay. And then I want an additional replacement, which is going to be opening caret, not right caret, any number of times, plus right caret, replace string, like this. It's telling me I'm missing, yeah, okay. Right. Okay, great. So do that to P. Valid input source. Oh, geez. We're on the next problem, man. Yeah, this removed all of the garbage, it looks like. And is this... Huh. Some of these commas look oddly placed. Well, whatever. Okay, so now we're gonna do opening brace, close brace, index of this string that I built. And we'll enclose that neg1, or sorry, 1, neg1, 0. Sum scan. And now I only want the opening braces. And those I can sum. And I get 9662. There's a bunch of things that could go wrong, but oh, this is the right answer. Okay, great. Now you're ready to remove the garbage. You need to count all of the characters within the garbage. Now that is annoying. Maybe I can partition it. Hmm. How many non-cancel garbage characters are within the garbage? Okay, actually this isn't that bad because this is just a length problem. So we can just do, so we replace all the canceled characters, right? And we'll call this PT. And now we're going to replace this is not star like this, quad R. We're just going to replace this with the empty in the opening caret like so. Length PT minus. $49.03. Hey. Alright, not too bad. That one was easier. So all that I'm doing here is I'm just saying Okay, replace out the canceled characters, and then take the length of that string minus the length of the string when you've substituted all the interim garbage characters with an empty string. So it's just length of the string before garbage cleanup, length of the string after. You just find a difference. So, all right, we'll put this one together. Which one was that? 9? Yeah, 9. I do want to create it. So that's just this. And then the parentheses nesting thing was this one. I'll call this one part 2. Wait. Actually, this one's fine. I can just do this. So we can call this P1 and P2. Then the answer to part 2 is going to be length P1 minus length P2. 9662 and 4903. Yeah. All right. Easy enough. I can kind of take this one out. Just to make it easier. But yeah, relatively simple problem. All right, I think that is going to do it for tonight at least. I'll probably do a few more problems tomorrow. And the day after that, and the day after that. So we'll see how long I can keep this up. But yeah, if you've tuned in, um, oh wait, we have some chat. Hello there. I did this one yesterday. Ah, yeah, 9. Had so much trouble with 10 part 2. Well, I'll be doing problem 10 tomorrow, so. Hashes always came out wrong. All right. Well, yeah. Thanks for tuning in, especially yeah if you're new to APL. Um, I hope that you've learned something. Some of these problems that I did today weren't honestly a great fit for APL, or maybe I just did them incorrectly. Um, that one, this problem, this problem was it 6 or 7? 6 was fine, I think. 7, this one, I really need to work on like graph traversals, tree traversals, things like that. I know how to do them in APL, but this sort of, when you get these sort of problems that say, hey, find the discrepancy in recursive weights between neighbors or whatever, that's the sort of thing that I need to work on. So, I mean, it's good practice, but yeah. All right. Well, I will be back at 9 p.m. Pacific. It's midnight EST. This is the same problem. They're the same time when the problems come out. So I'll be back then tomorrow. And if you've enjoyed today, I hope to see you then as well. But thanks for watching.